Well, welcome to this video on limitations of free energy predictions. We've seen in previous videos that free energy change, delta G, is incredibly powerful to show us whether reactions are feasible. But now we want to consider this question of, will a feasible reaction actually always occur in practice? So here is an example of a reaction, and here is the free energy change for that reaction. So have a think, should this reaction be feasible or not? Well, hopefully you all said it should be feasible. You're right, it should. It's a negative free energy change. That's the condition for feasibility, is that delta G should be negative, and it is. So this is a big negative delta G. This should be a feasible reaction. So I want you to watch a video in a moment for this reaction. I want you to think about these questions. What happens when the hydrogen peroxide is first poured in? Is that what you would expect, given that it's a feasible reaction? And then they actually add some solid potassium iodide in, and I want you to think, is that what happens when it's added and why? So click the link now to watch that other video and then come back. Well, what did you see? Hopefully you saw, perhaps surprisingly, that the hydrogen peroxide solution here doesn't do very much when it's first added into the container. You'd expect, producing oxygen gas, that you'd get lots and lots of bubbles. Now, if you do this in practice, you might get a very, very small number of bubbles at room temperature. But generally, the hydrogen peroxide is not really visibly decomposing at this point. Now, when you add some solid potassium iodide into this, you get some dramatic results. And this is just an example here of what you might get if you mix this with the detergent to stabilize the bubbles of oxygen and some food coloring. You can get some really, really nice results, and this is known as the elephant's toothpaste experiment. Now, why has that just happened? Well, it's important to note that in both cases delta G is minus 224. I'll miss off the units for brevity. So this has not changed the free energy change one bit. The potassium iodide has not done it. What it has done here is taken us from a slow rate of reaction to a fast rate of reaction. Now, how does it do it? Well, this here is a catalyst. And if you think back to what catalysts do, catalysts lower the activation energy. So the reason this rate is slow is because you've got a very, very high activation energy. And the reason that the rate gets faster is because the activation energy has been lowered by the catalyst, and therefore the reaction proceeds much faster. It was always feasible. It was always the case that these products were more stable than this reactant. But because of the high activation energy, it was very, very hard for that reaction to actually take place at a reasonable rate. Remember, the activation energy is like the sort of hill that you have to climb over. So the reactants and the products, if we imagine that we're plotting plotting the free energy G here, my reactants here, hydrogen peroxide, are higher in free energy than H2O and O2. But there's a big hump in the way. There's a big activation energy that needs to be overcome in order for this reaction to happen. And so it doesn't happen. What the catalyst does when it's added is dramatically reduces that activation energy, and therefore the reaction can take place at an appreciable rate. So where does that leave us as we finish? Reactions with delta G is less than 0 are feasible. This means that on energy or thermodynamic, another word, grounds, they will result in more stable products forming. But this does not tell us how fast the reaction will be. It's kinetics. This depends on the activation energy. So by rights, anything with delta G is less than 0 should happen, but it doesn't. So if you want to think about whether reactions will actually take place, you need to think about thermodynamics, you need to think about delta G, and kinetics, you need to think about activation energy in order to do that. Thermodynamics and kinetics.